Okay, how are you?
Good, thank you. Do we have any questions anybody wants to see to start things off? Worked out, or what's up? I hear crickets. Not literally, but all right. Well, that's hopefully a good sign. So I will start going through this part. The Newton's laws, clearly we're not going to go through them in as many details or as long as we did in grade 11. But there is questions underneath here for you to make sure you know how to do with grade 11 material. It's going to be a day or two more of that kind of statement until we start doing actual like circular motion and new stuff, right? In a little more detail. So just to remind you of the three laws, I'm never going to ask you like no one really cares which one's which, but once you're familiar with them, you remember which one's which, I guess, right? That's not a big important mark in the course for remembering which one's the second law or whatever. But anyways, the first law is the law of inertia. The idea that objects remain at rest or in uniform motion unless they're acted on by a force, right? Just inertia itself. And the idea, like we know that friction made it sort of hard for people to realize that because it didn't seem like objects in motion tend to stay in motion. It seems like they tend to grind to a halt. But we know that a property of mass is that it gives objects inertia. There used to be little flash things in here that made this lesson more interactive, but they are currently disabled. I'm hoping that they get them working at some point for us. So I'm leaving them in for now. But anyways, so basically there was a truck that was, driving along, and then the truck, I guess, hits a car and stops really fast. And so the ladder, basically continued to move because it wasn't tied down properly. So, picture a truck driving along with a ladder on the roof or something like that and hits something, and the ladder just sort of falls or stays going forward. And so it moves forward relative to the truck. This one had a hammerhead hammering down onto a wooden block. It just talks about, just think of the ideas of inertia, right? So if you had a hammerhead, something like that, whatever, and it's on the handle, and if it was loose here, you could move this whole thing down and smack it on the ground, right? And then the inertia of this part here, right, would drive it further onto the handle. If you wanted to, secure the hammer head onto the handle if it was loose, and then you can drive nails in the top here to spread the wood out. Like that's just using inertia to your advantage. So just a couple of little ideas like that we had to do this. This one again, maybe I should just start skipping these because they're not there anymore. But they had something being swung around in a circle. And it says what happens if you cut the rope while this hockey puck is being swung around. And so right now it has a velocity that way at each of these instants. It's going to have velocities at these, call them tangential velocities, or velocities along tangents along the circle. So if you cut the rope, of course, this thing would continue on with a straight velocity like that. Ish. I didn't draw it super straight, but so the answer was B in terms of this flash applet that might start working, but it continues with that velocity it had. So that's first law. Second law, of course, is what happens when you do push on something. So it's F net equals ma. So I think we're working with that one consistently enough in previous days and consistent next days or whatever. We're seeing that enough that I don't need to talk a ton about it. But I do want to just remind you of the importance of noticing this idea of F net and acceleration link, right? So in this question here, if you calculate it out F net as a number, once you get that as a number, then you can get the acceleration value, right? So you can see you've got an applied force and a friction force, and so you're going to say like F net equals blank plus blank, and you're going to get this as a value, and you're going to then plug it in and figure out what the acceleration would be, right? So this is very, very much review from grade 11. The page, it is all worked out here on this page. It shows, you figure out the net force. Eventually here they have this. The way this is organized isn't my favorite, but it is correct, I guess, right? So that's your FNet value. Let's stick with red, FNet, right? That's FNet. And so what they have in this line right here, you can see there's FNet equals MA. I kind of prefer to do a calculation and get FNet as a value and then say, oh, and FNet equals MA. And then you have sort of these two separate thoughts that are both important. But yeah, so you get the acceleration. And that's using Newton's second law. What's this one have? Oh, okay. Yeah, it's just, these are just being shown to you very quickly here, just to give you a reminder of some of the things you're going to need to be able to do, right? So if this is a kind of a review question that involves stuff we have looked at in more detail previously, or just recently, I should say. So this part here, of course, you can get like a delta V, right, or a V1 and V2, I guess, really, and displacement. So you can get acceleration, you can even get time if you wanted, right? So it's just a uniform acceleration question. Things aren't locked in place here. So this is a uniform acceleration question. So you can get acceleration, and then you can use acceleration to figure out the applied force, if whatever they told you here. So they told you it comes to a stop, and it's just a friction force that's causing it to come to a stop. And so that's your net force. So you'll see calculations there where they use the uniform acceleration stuff to get the acceleration. That's review. We've done that. Actually spent time reviewing that this course. And then saying, okay, well, the net force is the friction force, so F net equals ma, and so that friction force equals the mass times the acceleration. All right. Third law, of course, is the whole action-reaction force thing. For every action force, there's an equal opposite reaction force, and this is a different wording of what we saw in grade 11. And this so-called horse dilemma. I've never heard it referred to this way before, but if you're picturing a horse in a wagon and you have this like applied force of the horse on the wagon, and then wait, by Newton's third law, what's that here? Yeah, I'll have to define that. I got a phone call coming in, but I should probably keep teaching. So the applied force of the horse on the wagon, and then there's this equal opposite reaction force of the wagon on the horse. And the silly question here that it seems silly once you realize the answer to it, but really it actually is a bit of a stumper the first time you think of it. Why isn't the net force 0? Why is the horse able to actually pull the wagon even though there's an equal and opposite reaction force? Why don't those balance out? Do you remember the answer to that? Anybody? So I want you to picture the horse, pulling on the wagon, and the wagon pulling on the horse. And I've drawn my diagram in a way that should help you remember the trick as to why those two forces don't cancel out. Yeah, there's a force back on the horse from the wagon. Yeah, there's a force on the wagon from the horse. One's forward, one's backwards. They're supposed to be around the same size. I didn't draw it as good as I could. Why don't those cancel out? No? Well, it's a good thing we're mentioning this then. So they don't cancel out because they're on different objects. One's on the horse and one's on the wagon, right? They're on different objects. So they show basically a block, these two different blocks, and there's a force from block, the blue one on the red one, and there's a reaction force of the red one on the blue one. The free body diagram looks like that. And then you consider those two objects and you're like, well, one's forward and one's backwards, but yeah, sure, but they're on separate objects, so they can't cancel out. So that solves the horse dilemma, is that there is equal and opposite reaction forces, but they're always on different objects, so they don't cancel out. Something we can tie into what we've seen recently, electricity and magnetism and Newton's third law. If we look at the attraction force between them, we would have said, Fe equals KQQ over R squared, right? With the distance R between them. And so we originally just said, basically, that's just the attraction force between them. Sometimes you can be asked, like, just what's the force of Q1 on Q2, right? So this is force of 1 on 2. And of course, it's equal to, if you're trying to figure that out, you just look at the KQQ over R squared, right? It's actually the same calculation, whether you're talking about one or the other. So you can actually sort of think of this as, this is an action force, and then the equal and opposite reaction force is there, right? So force of Q1 on Q2, and then reaction force of Q2 on Q1, there's actually an action-reaction pair logic in this question. If we thought of it as like curly E, even force per charge, then you're just looking at KQ over R squared. And then it seems even, more where it's like you're figuring out these two different values, right? But by dividing out the ones, I don't need to complicate it with that one, I suppose, but I just thought it made it obvious. We had the idea of these two different forces, and of course they're both experiencing forces, so they're not going to cancel out. They're on separate objects. Just wanted to make that. Well, that didn't work at all. Anyways, just wanted to make them closer to the same size. That's all. It's better, except it's doing crazy erasing now. So never mind. I'm done. Yeah. So first, second, third law, all that stuff. So now the little bit of a new thing for us here, and we are tackling, is the idea of these equilibrant forces, or equilibrant forces, depending how you say it or where you see it. And the idea is that if a system's in static equilibrium, like it's got constant velocity or no velocity, right? No acceleration is the key. If the net force is 0. So I want to make sure you have time to maybe jot down a little more with this page, okay? These other ones were just fly through, review. This is a little bit new. So if we have two forces acting on an object, the blue ones, and we're told that it's not moving because of friction, then you can figure out the friction force, okay? And the idea is that the friction force is like balancing those, right? So big picture, all you really do is you add these up, figure out what that total force is, and then say, well, that's going to be the opposite. The friction is going to be the opposite force. Equal force in size, but opposite direction, I should say. So the idea, when you go to write this down, is essentially you're saying like, well, net force equals all of the forces added up on it. You've got the two applied forces, and you've got the friction force, and they're adding up to be the net force, which is 0. And so mathematically, the logic of saying that this force is equal and opposite to balance them actually comes out of the net force equation as well. So you end up saying like the friction force is the opposite of the other two added up. So it's leading to that logic, right? So you add these guys up, and then you just, if depending on what you get as a value for those, you just basically give the friction force the same size but opposite direction. So the opposite direction part, you have to kind of think through what that would be. Like if I don't remember what the numbers are offhand for this. I could look, I suppose, and see. But say this is an angle there, just theta. Let's just call it, right? Clearly, this friction force based on this diagram is like west 30 degrees south, right? Right. So that would have come from the opposite vector. Let's picture the opposite one being here from the sum of those two. So if that was F net, and then this would be the same theta. We got opposite angles there. So you have to try and add these guys up. This diagram is not as, might not be as bad as I'm thinking it is actually. If I did put these like, tip to tail out there, I get a vector like just way bigger, right? And so we'd have a way bigger one to balance. Anyways, so this one would have been like east 30 degrees, so east theta, why did I say 30? West theta degrees south. And so you can tell that one is that, but this one would have led to that by being east theta degrees north, right? And so this would have been your F1 plus F2. I almost said F by accident there. Right, so this is your F1 plus F2. And then, of course, the idea of the opposite of it right there. So yeah, like the east is becoming, west, and the north is becoming south, and it really does lead to the opposite. I just thought I'd pay attention a little bit to that direction thing because it can be a little bit confusing. But it really does just switch. But drawing a picture helps a lot too. So of course, to get the actual sum of these things, we'd look at components, or you'd look at sine or cosine law, which we've had a chance to review recently. So I'm just going to show this. But you've got, this is showing the tip to tail diagram. And then when you're adding up to get the overall, I'm tracing it with the mouse here, the addition of the two forces like that, you've got your components. You're going to have to add this component and that component, and, add them all up, right? So we keep track of the X's and the Y's, keep these separate, right? Separate, whatever. And so, yeah, your X components, let's look at your X components there and there. That's these two, right? And then your Y components. And so keep in mind the idea of your direction system, right? And so the fact that this one right here, we are going up, means a different color. So that Y component, we are going up. And so because that was an up, this is why this is positive, and then that over here was down. That's why that's a negative. But the component stuff is supposed to be reviewed and good to go now. But that's just, this is a page that has detailed numbers worked out for you if you're having trouble replicating this process. End result here is that over here you've got your overall. Wait, that's not the overall. So I would probably at this point encourage you to draw the regular diagram instead of the opposite one, which is what this part is. This is the kind of the opposite diagram. So you might be better off to show, your 28.8 and your up 8.28, and so then get your F1 plus F2 and get your angle, right? And then just visualize the opposite of that one, like this. And so that's where that logic there of, the angle in the opposite direction, both north and south wise, and so on, makes sense, right? So this is your negative F1 plus F2. So the size of these things, of course, would be the same, though, really, if you're just looking at the root of the sum of the squares and the tan inverse of the ratio to give you the size and the angle. So anyways, so I probably would personally, right now at least, apparently not in the past, but I would probably tend to do this first, get the actual vector, and then just flip it. Well, that's kind of what I did there, actually. So if you see, like I had the green one this way, and then said opposite is the other way. I just kind of like, at this point, I think it makes sense to have it sort of shown over here the opposite way, but the way I did it back then, I'm just noticing now, so I'll clarify. The opposite vector here, you could actually get this theta based on the parallel lines theorem, but I think this one's better. I like that one better. The idea of just showing it in the opposite direction. But however you want to communicate that, as long as you're getting results that make sense. And so you should be able to see this in the world around you, even, like the clothesline example from grade 11 that we saw, the idea of these two tensions adding up to the same as that gravity force if everything's balanced out, right? So you could show, F1 plus F2, let's grab this one, put them, tip to tail. And then so you've got your two, got your vectors, how they added up. And so then picture this gravity force and this upwards force balancing out, right? F net equals 0. Yeah. So whenever you're seeing that slack in the line, of course, that was the idea. We needed to have that, right? So it's an applet that showed that kind of thing. So you get into these examples here where you'll just need to practice this a bit. So let's look at this one here. Let's maybe cover up a little bit of that. Get you thinking about this yourself first, right? So if you've got a 30 Newton gravity force on that, you want to determine the tension or the forces in the two arms here. Okay, so with the sign being stationary, I should point out that you don't want to have an ideal sign construction here would have things built so that the force in here would just be a force. I'm just going to say that way just to keep it really general for now. Okay, so the force in there is that. So we don't have any like torque kind of forces going on here where there's like a twisting force on that bar. So I want you to think a little bit about this for a bit and try to calculate out, like draw a free body diagram and see what you can come up with for determining those two forces in there. And again, the force in this one's only side to side. The force in this one has oops, grabbed a weight pen by accident. The force in this one has the diagonal length to it. Okay, so you're trying this a little bit, right? I'm giving you a little bit of time for this. You're going to draw a free body diagram. You're going to figure out how you could solve for those forces. Give it a try. So hopefully I have a free body diagram like that one that you saw briefly before I covered it up. But certainly you've got your gravity force down of 30. You've got a tension force there that way. Now, if things are balanced out, if things are actually, there's no accelerations anywhere, you should be recognizing here that, you know, if there's no acceleration at all, so acceleration equals 0 overall, then that would mean that this way there's no acceleration, right? Acceleration in the x direction is 0, and the acceleration in the y direction is 0. Pen is not behaving well today. Mind of its own. There we go. Right, so we got those two ideas going on. And so what you want to do is you want to start to apply that in this context here, where you're like, okay, well then, you know, we've got in the vertical, let's circle this part. You're gonna look here and say, okay, well then this part and this part, supposed to be doing those curly brackets, but you know, you've got must have a balance situation there vertically, right? And then same thing here. The horizontals must be balanced out. So you're picturing this component this way, balancing this, and and same thing vertically with the sign being stationary and so on. So you start to try and work that out. So just like here, I'm pointing out, we've got acceleration in the y direction is 0. Maybe we should put it over here, but and acceleration in the x direction is 0. That's our driving, that's our starting point, right? So what does that tell you? If those accelerations are 0.
That the net force in each direction is 0?
You betcha. Good job. Thanks, Sarah. So the net force in each direction is going to be 0, and so you can start to actually add things up, right? So when I told you here that this horizontal bar has no force, that's sort of ideally, right? It could have been engineered poorly, and there could actually be sort of a torque force on that thing based on who knows what, right? But the ideal construction here is that it doesn't have any up and down component of its force. So we've got a net force in the y direction of 0. We know we've got a 30 down, and so we know the tension force, the component, a y direction component of the tension force in this F1 actually ends up equaling 30. And then horizontally, we've got the 50. What did that do for us here? Oh, I see what I did there. Yeah, so what happens next? You've got this 30, but that's the tension, that's the component, right? So as a separate thought afterwards here, you want to sort of use the fact that the component, right? The math for the components that 30 is, right? So ft itself, I'll just write it easier. So for ft itself, right, we know from this comes from knowing like ft y component equals ft sine theta, right? It's clearly what that is. Now that we're looking at it in that. All right, sorry about that. I bumped the hang up button on the microphone that's on my desk. Instantly logged me out. I'm back. All right. So that actually allowed us to solve for the tension force T1 by working backwards, basically having known what the component is. In 30, you can solve for what the tension force actually is. Anyway, so then at that point, you can say, okay, well, what else do we know, I guess, right? So we've got the x component of that tension force that we now know, and that has to add up with the tension force from FT2. So I put that in as a minus. Why are we putting that as a minus in here? Because it's to the left, right? Which then solves out to be a plus here, showing us that the force in that horizontal bar is to the right. So, yeah. Any questions about that one?
What were we calling theta again? I'm not sure. I have it in my diagram.
Oh, theta was actually given though. It was a 35. So yeah.
Oh, okay. I thought we were solving for a new one. Okay.
No, not the. Yeah, in this one you're given the construction of it, and then told you're asked for what the forces are going to be in there. And this is like an engineering style question, right? Where an engineer needs to sort of know what the forces are, and then they'd look up the charts for like what diameter of a what size of a metal bar you need in order to withstand those forces. Clearly, if you hung a heavier and heavier sign here, at some point you're going to exceed the the breaking strength of this material, right? And so engineers need to be able to calculate the actual values that these would have, and then choose a material based on that value you need to be able to hold. So these can look weird, you got different examples here. Like you've seen stuff like this around you though. Like sometimes there's weird streetlights where there's this bar here, and it's a cable holding it here, and just looks kind of weird. But it's, I don't know. Want to try it? I'll give you some time to try it.
Sorry, can we just go back to the last page? I didn't get the rest of it. I'll just take the picture.
Sure. Just that part?
The calculation part.
Yeah, I think you got it there now, right?
Yeah, that's perfect. Thanks.
Okay. You're good to go then?
Yeah, I'm good. Thanks.
All right. So calculate forces, determine the tensions in the arm AB and the cable CD. I think in another slide somewhere along the way, I do talk about the idea of you can't push on a rope. That's a common engineering saying. If this is a cable, then that would mean that force can only be, right? You have to sort of watch and think, okay, force can only be to the left, right? So the idea, if you can't push on a rope, I'll mention it. It'll come up in another slide. I remember writing it somewhere. But so my brother-in-law is an engineer, and he was working on a project where there was a pipeline in underwater, and there was a pipeline, and it was held in place with like cables, so that when the pressure was changing in this pipe, it wouldn't allow it to flex, and it kept failing. And they were trying to figure out why. And it turned out that the force was in the opposite direction that they were anticipating, in an area like just what they had thought. And so maybe in this area here, this thing's trying to pull this way, but when the pressure came on, it actually tried to push that way. And so they were calculating out and being like, oh, that cable should be able to withstand the force there. Like, it's why is it failing? And they realized, oh my God, it's literally a, you can't push on a rope situation, because they were expecting that cable to push the other way. So anyways, when I mention that in another slide later on, I'll say, like we talked about before. So in case you need it, just recognize, as hints go here, this is the same as that. Okay. There's not actually any difference that it overhangs there and stuff like that. That just sort of doesn't really change anything. And what's here, number 2. Obviously, for each x and y direction, separated out. Accelerations are 0, f net 0, just like we looked at on the other page. So I'll give you a little bit time for that. Ooh. All right, I'll start to reveal a little bit here. Looks like first step. Maybe I should use white squares here, just to guide us through this. Just don't have it covered up. Something like that. So what do I have there? The forces. I think I'm showing the gravity force, obviously, is the 294, so Fg equals mg. And then we have forces involved. Not sure why I drew it quite like that, to be honest. But the main thing we get to soon is the idea of acceleration. Right, so acceleration in the y direction is 0. So what I have there so far, I have that force there, and then I'm showing basically the idea of the components, but usually I would just do that when I get to it later. So this might be where you started, right? The acceleration in the y direction is 0, and so the net force is 0, so the net force in the y direction equals the gravity force plus the AB force y component. I just actually calculated some of those component logics first, that's all. So you would end up with something like that, where you've got the little blurry there, but the 294 down is combining with the, FAB, picturing this force up here. So I get showing on this one. We'll just grab red maybe here. We've got this force here. And so if we want that y component, we've got the 37 degrees here. And so we're talking about the sine because it's opposite side, right? So FAB sine 37. And so that's going to allow us to solve for FAB. We're just going to add 294 to both sides and divide by the sine 37, giving us a force in the diagonal bracket, diagonal rod there of 490 newtons. Okay, and then clearly the next step is acceleration in the x direction is 0. So we're going to be calculating the x component of that force, FABX, right? And then basically setting that to be zeroed out by that tension force in that cable. So acceleration in the x direction is 0 also, so they must be balanced out, and so we've got F net equals the x component plus that cable force CD. This is going in as a positive value because it's to the right, right? And so then we solve. We've got the cos 37, of course, for this part here because we're adjacent to the angle. And that gives us the off the page a little bit here. Weird. Yeah. So the 391 number there, it ends up being minus here, which means to the left. It was missed actually in the writing there of it, but yeah. Therefore, the forces are blah, 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 right? Just stay there. All right, moving on. Do we need that page a little more? What do we got? Maybe I'll leave that one for a touch more for you. Anybody need it still? No idea how long I need to leave for this stuff, so no one's keen. Their mic and saying they need it, so here we go. We have mass suspended by 2 cables. Determine the tension in each cable. So hint is here, of course, we still got an equilibrium situation. We got acceleration is 0, saying it's suspended. It's implying that it's an equilibrium situation. And so we're going to try and figure out the tensions there. So hint for this one as you try and get started on it, right? Don't make assumptions about the relative sizes of the forces. The math and the algebra that you work out will dictate the values, right? You can't say, oh, F1 and F2 and these 2 cables are the same or something like that automatically and hope that it's true. In fact, in this case, because of the angles, they're not going to be true, right? Because it's not centered. So you just got to let the math determine that for you. So give that one a try, please.
Mr. Horn, you're muted.
Sorry about that. So I was miming here for you, apparently. But yeah, obviously we know the x and y directions, there's zero acceleration, so zero forces. It might lead to sometimes, or you have two separate kind of situations and two equations that kind of mesh together into a system, and that's when the two equations, two unknowns, linear systems type thing kicks in for you, right? So let's take a peek at what we've got here. So obviously there's the free body diagram you probably would have drawn. And you could have drawn a diagram where the forces wouldn't have been right in right proportions. That's okay, right? These are just representing the angles there, the 30 and the 40, right? But this one being, on a more of an angle, it's providing more of the lift. It's going to have the bigger force and so on. If you get that, if that was intuitive for you and you drew it that way, great. But it's not mandatory. Then the math is going to dictate the sizes in the end. So the idea that we're going to have the horizontal forces canceling out, you can tell in this diagram right away looking at it that the only horizontal forces are an FT1x. Stop moving around on me. FT1x. Goodness sakes. And then the other one over here, we're going to have the FT2x. Right, those two forces are going to add to zero. We're going to have a net force equals, acceleration. Net force is zero, and you're going to add them up because there's no acceleration. So that's going to certainly be that's going to be equation one basically, right? And then we're going to have a vertical component, so a y component of ft1 and a y component of ft2, and those are going to add up with this one to be zero, right? And so that's going to become equation two. So let me get to the point where we have some of that going on. I feel like maybe I might just do this one. I'd like to just draw it there from scratch, but oh well. So what do we end up with? Maybe you can picture that or draw it yourself or whatever before we move down. It's easy to but easier to visualize all these forces, right? If you've got a diagram to refer to. So here we go, right? I'll just put that guy back there, I guess, for now. So the x direction stuff, we were doing the x one because it sort of stands out very obvious. It was the first one I drew as well. I don't like the subtraction listing in there. I more put it when the numbers go in personally, but it's the same thing essentially. In fact, I guess I'm sort of having to put it in there anyways because it's always going to be a variable, right? So I prefer when the numbers kick in, but anyways, so this one, of course, is going in as a negative here because it's to the left. How do I want to do that? Probably just this part here, right? Saying because it was to the left. So that's FT1, right? In the diagram to the left. And then the other one is positive because it's to the right. But we've got an F, we don't know that these tension forces yet. We don't know FT1 and FT2. So you have to just list as FT cos, FT1 cos 30 and FT2 cos 40. Those are just your components. Right? These are both adjacent to angles, right, for those x components. So we end up with an equation. Really, to me, it's kind of like that's equation number one. They're solving that one out in advance, but I think you probably, with the way your math training has worked out, you might just have that as an equation for now. You're like, two unknowns, right? Based on that, as soon as you have that, you're looking for another equation, right? So you need another equation. And it probably ends up with two unknowns as well, right? So basically their step here is getting ready for substitution, which I don't really necessarily think you would have started to do that yet at this point, unless it's just sort of how you're going to approach this kind of question. Oh my God. There we go. So they solved for FT1, whatever, but the other one, let me communicate this a little bit better here. This, or add to this, right? This one is the y component stuff. Ugh, I should have modified this page a little bit more. So this one, oh, that's just the same stuff. Yeah, two unknowns. Yeah, so we can't solve, of course, so you need another equation, like I was saying already. I just forget what I've mapped out in advance and what I was going to do on the fly. So anyways, you're good with that part. That's just the x direction stuff canceling out. Next step is, of course, the y direction stuff cancels out, right? So we've got net force in the y directions are going to add to 0. So when you're thinking, okay, yeah, you've got your net force, you've got your gravity, you've got your whatever. See, this is like the minus going in there is a little bit, I don't particularly like that, but anyways, we know this is 0 because everything's canceling out. So that's going to be in the next line there. So we've got the negative gravity number put in because we know the direction of it. And then the other two are going to be solved for, they're going to be up, right? So we end up with really FT1 y components, FT2 y components adding up to this 19.6. I definitely want to see the angles in that one, of course, right there, right? So that's your equation number 2, where you're saying, oh, there's another equation where we have two unknowns. And so you're going to work with both of them, right? So putting them nearby each other, of course, this FT1 value here, this FT1 value here, I'm showing that it gets substituted into there. And that's your substitution. That's your substitution step. So there you go. So that leaves you with an equation where you just have, you would just have FT2, yeah, FT2 that you'd be solving for. They solve both of them for FT1 and then equate them, which is kind of the same thing. But the substitution process, just boggles my mind how ugly some people can try to make this. Maybe I'll just go to a new slide here for you. Carry this out a little nicer. So equation 2, equation 1, basically here. I'm gonna grab that 2D slide. So that gives us a 19.6 equals, and we've got the 19.6 minus FT2 sine 40 over sine 30. Just plugged in there, right? So that's times a sine 30 as well, plus an FT2 sine 40. Now, before you start to just, get decimal values and things like that, save yourself a little bit of time and notice, be like, oh, geez, if we're multiplying by sine 30, if we had a divide of sine 30, those are just going to cancel out. So we're going to have a 19.6 equals here, because that's gone, you don't even need that bracket anymore. We've got a 19.6 there, and then minus an FT2, and get what sine 40 is as a number, I suppose, and plus an FT2 sine 40 there as well, and so on.
Mr. Horn, for what you're doing right there, have you already subbed in the other equation?
No, you know what? I'm noticing. I was just actually looking at this thing. Wait a minute, because this is all going to 0. This is going to lead to 0 equals 0, because what I've done by accident is I plugged equation 2 back into equation 2. We don't want to do that. We want to plug it into equation 1. So this was from the other one. I need to put this one in. I just botched it just here right now. So let me fix that. That means that's gone. And that's gone. Right idea, just wrong one went in. But sometimes that happens, you know, and what I was noticing there, like I said, everything is just literally just canceling out and giving you eventually 0 equals 0. That's a good hint that that has happened. So this is the sine 30 from the original equation. And then we have here the ft to cos 40. I had it written right, but I just didn't realize it. So nothing's canceling this time, because obviously not everything's canceling out, but we're just going to have to calculate numbers. If you wanted to save yourself a little bit of time, you could do tan 30 instead of sine 30 over cos 30. That's the same from your trig identities stuff. But these cancel out. So at this point, you're just getting a 19, darn it, getting a 19.6 equals, and there's going to be a number with ft2, and plus this one's going to be a number with ft2 just by calculating. And obviously here we're just going to solve for ft2. Does that make sense? I don't think we need to worry about the algebra too much at that point, but that's your substitution process, right? Substitute 1 into 2. Not 2 into 2. That's no good. So it just messed me up that this was there for no reason. If we're actually just substituting 1 into 2. Anyways, that is equilibrium force stuff. Okay, so sometimes you end up with 2 equations, 2 unknowns, complication along the way. So these questions are, there's a lot of them, but this is literally just the grade 11 review stuff. So you're gonna look at those, you're gonna say, oh, yay or nay if you need to review it or not, right? The equilibrium force stuff with the big yellow star is the stuff that you really want to make sure to do. And there's only 1, 2, 3, 4, or 5, 6 questions, whatever it is, right? In question number 6, you can try to do part C first. Mind you, even if you did do part C first, you should recognize that you could just do it based on this idea here of equilibrium force. But they actually set you up for in part A, part B, and then you use them in part C. My solutions, I misread the question. That's why I'm putting this as a recommendation. But so I actually just did the question from scratch, where I solved for the equilibrium force directly, and it involved some grade 11 math skills that I think you should look at it and say, okay, yeah, like I could power my way through that if I had to. The way the question's set up, though, they're giving you like a force. They're giving you a force this way, and they're giving you a force this way or whatever. And basically the idea is, these add up to the other one. And so you could just do it based on the direct, what we talked about in this lesson, that they add up to the opposite. But I think it would be a good exercise to look at the process of solving it in a different way as well. So that is equilibrium. And the other stuff was going to be just applications of Newton's laws. And again, the vast majority of this is review. I feel like maybe I might even want to just go down to where we start talking about apparent weight and problems with pulleys. But I'll just show you the pages that are here to help you. Obviously the problem solving process, that. But this is too, like, I can't, this is too much of a review for me to go spend a ton of time going through it. But you want to be able to do this, of course, right? So what are you noticing here? As soon as they say a constant velocity of 18, you better be saying to yourself, ooh, F net equals 0 as a driving concept in this question, right? And they told you that there is a force of 85 newtons forward, and it's going against gravity, or against friction, I should say, sorry. And there's, what all they show on here? So contractors moving across the floor. Yeah, force of gravity's down. Force friction force. Yeah, I'm thinking at this point, I'm thinking that the gravity force was a red herring. You don't need it. But given information is given, converting to meters per second and so on, right? I guess they just ask for the normal force. They're asking for the normal force, so they've given you information. More as a review, just for getting used to the idea that you need it. If it's traveling with constant motion, it's easier than the average question. I was thinking it was a harder question than it is, but they're showing like normal force up and gravity force down, applied force forward, friction force back, and they're all balanced, because of this idea that we have this net force is zero stuff going on. So make sure to look through the question and know that you can solve for the friction force being the opposite of that applied force, because this usually I just start with this one right here personally, right? Net force is zero, so add to zero. So that one definitely, I think it should just bounce through there. Trickier kinds of cases, it's a slight trick, but we've done it in grade 11 as well. So read this one quick here, 75 kilogram box, and it's on a ramp where the angle is 35. Actually, no, maybe we haven't done this one, right? Because it's a ramp situation. I don't think we touched on ramps much in grade 11. Slides down the ramp, experiencing a friction force of 255 newtons. What is the acceleration of the box down the ramp? So these lessons are designed to be like a do it on your own kind of thing. So that's why it says try and then check on the next page and so on, right? And then give it a try. So basically, I want you to do that right now, I guess, right? And then we'll go through it. So start by drawing a free body diagram. You could draw a ramp itself, right? You could draw a ramp at 35 degrees and so on, right? But you're probably just going to draw a free body diagram with a gravity in it and with a dotted line indicating that there's a ramp in the situation to remind yourself of it. And if it's sliding down the ramp, then the friction force is the other way. And I'm not really trying to draw the sizes at this point, because the sizes, the math will determine all that for us. Yeah. So we just want the acceleration. I would probably add on to this plus what's the normal force, just to get you ready for the kind of things we need to be able to do as well. So maybe we'll add that to the mix as well. So trying that for a couple minutes.
Does the FF represent the friction force?
Yep. Yeah, and we know it's up the ramp because friction always goes in the opposite direction of your motion, right? So because we were told that it's going down the ramp with a velocity, then we automatically know this direction opposes the motion. So we've got that, it's 255. We've got gravity is based on the 75 kilograms, obviously. So that should allow us to get the normal force as well. And obviously we need it for the acceleration as well. So if you're on track here, you're recognizing that a component of this gravity force is in the direction of the ramp itself, right? So clearly the way this diagram is drawn, things aren't to scale, because we're going to need to have this component be bigger than the friction force, which means the gravity force must have been bigger just when you start to try and correct things, right? So we've got a gravity like an FGX, right? So one thing else I'm hoping you've done by now is you've defined a direction system like that, X and Y. So X down the ramp, y perpendicular to the ramp. Okay, so the direction you're actually moving or accelerating is your x direction. So we would, of course, do mg here for this. So we can say, oh, we can actually get that gravity force. So we've got 75 times the 9.8. I feel no need to put a negative in at this point because my arrows clearly are presenting down and so on, right? And later on in the calculations lines, you'll have to know to put it as a minus, but I'm just going to say 735 newtons. And so I think you should be at the step now where you're saying that we have F net in the x direction equals FGX plus FF. So we can just calculate these things. So we have the 775, and then we have what component here? So we know that this is the angle of the ramp stuff coming at us again, right? So we know the angle of the ramp's 35 degrees. We need to determine 35 degrees there. What angle are we talking about for the component of gravity? So we've got a triangle for gravity that's like this, right? And so we need to get straight what angle we're talking about there for that. If we're at a 35 degree ramp angle. And so looking at it right now, it appears that we would be the other angle, right? So like 180 minus 90 minus 35. Does that make sense? So I'm just going to do the 90 minus the 35 to get that number, right? So the 90 minus 35, 5 would be 40, so 55 degrees. So it looks like I'm looking at cos 55 degrees. And then we were told, now this is in the direction of the ramp, right? This is down, so that's positive because it's in the direction of the acceleration. And then we're saying, oh, and we have friction force. This is where I'm going to put in a minus like this, where I'm saying, and we have this other force, the minus 255, because it's against the motion, it's in the opposite direction. So we should be able to do 55 cos times 775, giving us 4.
Isn't it 735?
Good correction here. Yes, it is. Thank you. My scribbles are getting the best of me here. Thank you for the correction. So let's fix that there. Fix this part too. So we got 735 cos of 55. 55 cos on my calculator times 735 is 421. So I got 421.57 ... I'm gonna keep, like, I would have to round that to 421.6 or 421.8. Sorry, 421.58 here if I was rounding. I'm actually gonna keep a bunch of those numbers, so I'm gonna show it like that. And then I of course take away the 255. So my answer is my calculator. I'm just taking away 255, ending up with 166.578. ... So if I'm rounding at this point to, looks like maybe the lowest we had was 2 significant digits. I suppose what I'm saying there is, believe it or not, 170. If I'm done the question, that's the 2 significant digits. Because if I'm doing more calculations with it, though, certainly I'm going to use this number for calculations. So it looks like we've got the net force, right? So what's our next step? If we want to know acceleration.
F net equals ma.
You betcha. F net equals ma. So we've got a 170 down the ramp in the positive direction. We've got our mass of 75, and we solve out for acceleration. So that 166.578 dot 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 in my calculator gets divided by 75, and I get a value here of 2.221 dot 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 whatever meters per second squared. That's my acceleration value. So then maybe at that point you say, oh, okay, so 2.2 meters per second squared as an acceleration, actual value that I'm looking for to 2 significant digits. You know, the amount of numbers and digits you can trust quoted once you have sort of your final answer, right? So let's add on here plus Fn, that normal force. That's going to be good for us to recognize that we have to get that as well. It wasn't asked for specifically, but I think we should consider doing it. So that one, I meant to do that in purple here. My computers, maybe I messed that one. Yeah, see, I clicked purple. I'm just not quite hitting it, I guess. Anyway, so the vertical component and then the normal force, right, balance out. So basically in this direction, acceleration in the y direction equals 0. And so F net equals the normal force plus the y component of the gravity force, and that all goes to 0. So we've got 0 equals the normal force we're looking for, and then plus we have to put in the logical value for the gravity. So that would be what? If we're using this angle here, the 55, then we're talking sine of the 55. Right? If we're using the 35 from the ramp there, then we would use cos of that number, of course, right? So we've got our 735, and we had our sine. I need the thinner pencil here, sine of the 55. And I'm also going to put that as a minus because it's in the downward direction, right? It's in the opposite direction of this y direction that we've labeled before. So I wonder if I can get away with just doing this to make it easier to read. There we go. Yeah, so basically our normal force ends up being, I'm going to switch to blue just to make it easier to read right off the bat, ends up being the 735 sine 55, obviously. So 55 sine times 735 gives us 602, you know, point something, right? But whatever. So I guess you'd say 60 times 10 to the 2 newtons if we're talking 2 significant digits. So we don't need that one right now, but this will be used soon for friction. So this is needed to calculate friction. I'm actually going to point out friction coefficients. Remember the mu thing? So you need that number. So good practice right now while we're going through things in detail. All right, so let's we'll just skip all that because that's already done. And example 2, so this is the one where we're pulling at an angle. This is the one that's a little bit more review, actually, that I would just say let's just look at it together. So we're pulling at an angle. We've done that in grade 11 a lot. It was the ramp that we didn't do as much. So we're pulling something with a rope that makes an angle of 40 degrees. Obviously, we're kind of lifting on it a little bit, which is going to reduce that normal force. So the mechanics of, the process of figuring that out, I want to make sure you're reminded that you need to know how to do this, right? So if you're asked for the normal force, that was the idea where you'll need that normal force if you're calculating friction values rather than being told friction values. level 4 using a rope. It's a friction, yeah, instead of being given that friction force, you'd be calculating. So first you would get the normal force, calculate friction, and then do this kind of work, right? So anyways, the idea is we're lifting, so we've got a component up and over and so on, right? And so our X direction stuff, we can figure out that net force because we were given the applied force and the angle. So this is just the component of right there, right? Component of that applied force, put it in, we got the friction force, we can get the net force. And so we can get the acceleration. If you're asked for the normal force, then the normal force on the next page where you're saying the acceleration in the y direction is 0. We're not lifting the thing, right? And so we've got the acceleration in the y direction adds to 0, and you've got your gravity, you've got your applied force in the y direction, and you've got your normal force. So that's the one where, you know, people might forget to draw that normal force, but of course there's a contact force between the object and the surface that it's sitting on, right? So you've got the gravity force, you got the lift force plus a normal force. So just watch that normal force. Don't forget. Don't forget the normal force. So don't forget. The force of the chair you're sitting on right now on you to stop you from falling, that's your normal force. So again, the logic of it was reduced by an upward pull. Makes sense if there was a downward push. If this was a minus value, right? Picture if this thing was a down, right? So if FA was down, picture how that would be a minus value, which would make a bigger number here, right? Because these would combine to be a bigger number. So this would be bigger. And that would be like your normal force was increased because of a downward push. So that's big time just review of grade 11 stuff that we've seen. The author's solution left there for you to look at if you want. What I really wanted to make sure to talk about right now, because it's a little different for us, is this, these questions, we're getting into here about apparent weight. And so the idea is to picture being on an elevator on a bathroom scale. If the elevator were to like try to accelerate upwards, even just standing in an elevator yourself, if the elevator accelerates upwards, sometimes people get a little seasick, almost or nauseous from it because it's sort of weird, right? And so you're going to feel extra force kind of like pushing you up, which actually makes you, as they say here, feel heavier. And if the elevator is accelerating down, then you feel kind of lighter for a minute. It's this apparent weight stuff we want to talk about and be able to understand. So they're saying picture being on a bathroom scale where you all of a sudden bend your knees to squat down. If you do this, if you have a spring scale, I'm not sure if it works as well on a digital scale because they don't give you constant readouts, right? They'd have to have an old school spring scale, bathroom scale. So that's becoming less and less common for people to be able to do this themselves. I have one in 124, of course, for us to play with if we ever end up in there again. But as you squat your knees to fall down, you'll find your weight, your force upwards, your normal force, this is reading, right, will drop as you're falling. And then if you're extending your legs up to accelerate up, you'd get a larger value briefly. Okay, so this is what we're talking about being able to sort of calculate situations like this. Just little spoiler alert kind of thing going on here. When we're talking about reference frames like an elevator, that's accelerating, we actually are starting to talk about, unofficially here, non-inertial reference frames. And I just want to point that out because to connect these two ideas together and make it make more sense to you is the goal here. You're going to see that these non-inertial reference frames, where the reference frame you're saying, oh, my motion relative to the elevator and so on, that elevator, if it's accelerating, then you'll end up having different forces, right? So there's going to be different force values than if the reference frame was not accelerating. And that can actually lead to people thinking there are forces there which really aren't there, particularly when we get to circular motion. So that's my goal, is to help you understand this better by the time we get to circular motion. So when we do a question like this, okay, so we've got when it's not moving, I'm just going to show this one because this isn't the hard part, right? If we have a not moving elevator, then we've just got normal stuff. We've got a 50 kilogram person, we've got net force is 0. There's no acceleration. Everything's just normal stuff. So we got a 491 Newton. That's just your normal force up. Same as if you're just, a 50 kilogram person standing anywhere. Okay, so you got your 491 Newtons up. So definitely okay with that. You need to be okay with that first. The next step is when we talk about the accelerating elevator. So if the elevator is accelerating up at 1 meter per second, what happens? So for this one, let's point out some things. Okay, so I guess we have to sort of, what do we have to do here? We have to say, okay, well, we've got acceleration. Don't want that one. Right, got that. So, right away, what can we figure out? If we're told the acceleration and we told the mass, then
The
we
net force.
get the net force, exactly. So let's write it like that. Let's say F net equals MA. And so we've got F net equals 50 times a1. And so we've got a nice easy number here of 50 newtons. Oops. Easy as long as I actually write it. So we've got a 50 Newton up net force. Is that right? Yeah, it must be, because we got acceleration, we got that, right? So we've got that. And then if we analyze things further, they're saying, like, what's the reading on the elevator? What's the reading on the scale, right? If the elevator is accelerating up. So what they're asking for there is they're actually asking for the normal force. And that's maybe something to recognize in its own right, right? So we have to start to figure that out. And so we're going to picture like a free body diagram here where you've got obviously the gravity force and you've got a normal force, right? So I'm just going to like draw it like this for now and say like, okay, I don't necessarily know the size, so I'm just visualizing that we have these forces on this person. So let's go with F net. Obviously, this is all kind of y direction stuff, right? So I'm not really bothering to say F net in the y direction because it's all y direction stuff. But F net equals, there's a gravity force and a normal force. So normally, this would be 0, right? But now we're talking about a situation where this isn't 0. Instead, it's equal to 50 up, right? Positive 50 is up. So we've got a gravity force down. I can jump back and grab the gravity value from the previous slide, or I can just plug it in here as the 50. So we've got a 50 and a 9.8. Now that thing's down, right? So we're going to say, okay, that's down. We're going to put a minus in there. And we're going to solve for that normal force. Okay. So what this does is this must be our 491, right? From the previous thing we looked at. So that's a minus 491 down in the gravity. We've got our net force of 50 up, which is giving us a normal force of, let's just show it even right now, where I'm adding the 491 to both sides, right? Basically, you can see we've got more of a normal force than normal. Right, we've got that 491 plus the 50. So 541. So we've got a bigger normal force than we would have if we weren't if the elevator wasn't accelerating. So what's our, we should include that, right? This is a larger Fn due to the acceleration of the elevator. That's actually a non-inertial reference frame. You're ending up with more force. So I just want to point out the textbook and like wherever you're getting this from normally might not show this, but I want to just jump ahead to make the connection to what we're going to see. So we're noticing there's an additional 50 newtons up on the person. So that's where we're agreeing that it would feel like you're being. I think people would agree that it feels like you're being pushed into the floor by like an additional 50 newtons of force. You got this like imaginary force that's causing this situation. So, you know, in an inertial reference frame, if there isn't anything going on, you've got a 491 and a 491. And of course, this would balance out to 0, right? Acceleration equals 0. In this non-inertial reference frame, what we've calculated is we've got a 541 and a 491, and we know that there's an acceleration, right? So there's an acceleration, and so there's a net force up. F net equals 50. So we've got like an additional 50 up, right? Picture this as the additional 50 up, let's say, and it makes sense because we're accelerating. But if you're trying to picture the forces in relative to the elevator itself, okay, if you're inside of a room and you didn't know that the elevator started to accelerate up, you didn't know you're in an elevator, let's say, or whatever, right? And all of a sudden there's extra forces on you, it would seem like there's an additional force down on you. This is what we're talking about, but it feels like you're being pushed down by an additional 50 newtons. So in other words, what I'm saying here is that these would add to minus 541, and it would lead to no acceleration, right? So this is the acceleration equals 0 case, and think of that as like relative to the elevator. That's supposed to say elevator, right? So relative to the elevator, clearly you're not accelerating. So in the reference frame system of the elevator itself, this is the correct diagram. This is the non-inertial reference frame diagram where you're like, I've got 541 up and I've got 541 down. That's why I'm not accelerating relative to this elevator floor. Okay, so you've got a free body diagram for that 0 acceleration, thinking of the elevator as your reference frame. And then you've got this very logical as well. I should actually say the 2 different versions. You've got this very logical one as well, where you're like 541 and the 491, where you're like F net, of course, equals whatever it was, 50 newtons, right? And an acceleration of 1. Like that makes sense too. This is kind of the bigger reality, but when I say reality, I mean like relative to Earth, because the elevator is accelerating relative to Earth, right? So yeah. So I just want you to have your first little kick of the can here of like thinking of this like fictitious force, they actually call this. It feels like there's an additional force down on you, right? Really what's happening is the normal force is bigger. This green diagram, really what's happening is the normal force is bigger, providing this net force up, resulting in an acceleration up. But within the elevator, you absolutely do feel this additional force down. The bathroom scale would, of course, confirm it. So that's a little weird. So that's just the solution that I showed last time there of on the file itself has, you know, fnet and so on, and we calculate just like we did. Anyways, so I'll leave that in case you want to see both versions. So like, what if the elevator was moving but with constant velocity? What's that telling you right now? Constant velocity, therefore
Acceleration is 0.
Stuff, right? So we have acceleration is 0. So that is going to be the exact same. The pages after this will show it, but that's going to be the exact same as the calculations we would do for this one, right? Where it's like, you know, you're not moving or you're moving as constant velocity. So this is the same as V0. So same as V0, A0, right? You have to have both there to be clear, right? What would the reading be if the it's slowing down? It's slowing down at a rate. That's now acceleration equals negative 1.0 meters per second squared, isn't it? Right? We're accelerating the opposite direction. We're still going up. So that's a velocity, that's a positive value. Stop moving my stuff. All right. So positive velocity, and then a negative acceleration means they're slowing down, right? That's the idea of 1 grade 11 that we've talked about. So we'll confirm C, of course, is the same stuff, right? C is the exact same stuff. Where you get the 491, like it's, you know, since we have acceleration 0, it's literally the same page of calculations. What happens in the down case, though? In the down case, we've got a net force of 50 down, right? So you're going to see in here F net. What are we doing here? Just looking how they showed it. So they did the F net. That's fine. I don't like their sign game there. So F net equals Fn plus Fg. We're saying we know this is down, so it's minus 50, and then Fn equals, you know, we got here the minus 491 for the gravity. Stop. Changed my. All right, so we've got the minus 491 in there. So I'm just plugging in the values that we know. That should go there. And then, so yeah, we just end up adding the 491 to both sides, right? And so that leads to, over here, basically a 491 take away a 50, right, doesn't it? So you got a 491 take away a 50, and you get your 441. Right? This is less, right? This is less due to the acceleration. So now you got a free body diagram that looks like this, where you have a gravity force and you've got a normal force that's less. Right, so you've got a 491 down and only a 441 up, right? So basically, that's, you know, you're going to feel like there's less force all of a sudden. I guess eventually, if you get to accelerating down at 9.8, you'd have 0 normal force on you, and then you're in so-called weightlessness, right? Yeah. So there's that 441. I don't know. It bothers me the way that's shown there, but all right. Questions? All right, so there's another page there showing more examples to do with that, but we've done enough of that. So problem solving with tension. So these tension instead of normal force. So this one isn't the one that I need to do as much. This is, you know, cranes being lifted. That's a tension force instead of a normal force. So I'm just going to reveal all this stuff and show it's the exact same. They gave you an acceleration, so of course you can calculate F net. And let me just reveal that quick. Get to the better ones here. So F net, of course, equals the sum of all the forces. Like, this is literally the same calculations as if we're talking about an elevator. It's just, instead of a normal force, we're talking about a tension force. So, you know, work through that, make sure you can do that, of course, right? The weirder ones we need to be able to focus on. There's a something called an Atwood machine. Basically, it's a pulley with 2 masses hanging on it. I don't know why they call it an Atwood machine. Yeah, to do the calculations for this one, I'm going to walk you through it because it's weird and different. And there's a couple little tricks. The main trick, actually, is that when you figure out, let me just put it this way, the main trick is that once you figure out the net force that's happening in the system, you have to recognize the net force acts on both masses. F net acts on the combined mass. That's the most common thing to miss and therefore, you know, get everything wrong. I've done it myself. Okay, so watch for that. So you'll see that in the solution. Let me get to it in a second here once I get my computer to start behaving. There we go. So this solution I'm not as fond of. I want to just show you the straightforward way of doing this. Okay, so the first trick I'm going to show you is that you can define your direction system like that. It's kind of weird, right? But it's like basically the direction that the cable is going to go, right? The cable is going to go up on this side and down that side thanks to the simple machine called a pulley. they say that very similar here. They say, you know, the direction system, let the direction system be positive, be like away from the blue and towards the red. Essentially, they're saying what I drew is just a lot easier to see. Okay. So when you're analyzing this out, you can see you're going to have a larger gravity force here than here, right? But as far as net forces go, you've got a gravity force from one and a gravity force from the other. One of these is positive, one of them's negative, right? So the FT2, or FG2, sorry, is the bigger one. That's going to be the positive value. And once I put numbers in here, you're going to see it, right? I have this one in the positive, this one in deliberately as a negative, because it's in the negative direction. You've got a gravity force here. So this is FG2 that's acting in the positive direction. And then we've got FG1 that's acting in the opposite direction, right? So this is this is still your positive extraction reference here, right? As we said. So that positive extraction business means this is in the negative direction. So yeah, green, whatever, it's down. Right? It's in the opposite direction. Now they're both down actually though, right? So just recognize the weirdness of this. But I don't think that's too hard to understand the main idea of it, right? Where you're just like, well, okay, these guys are going to, you know, combine to be a net force of 88.2. The two gravities are working against each other. So we have a net force of 88.2. Anybody need time with that for a little bit before I keep going?
Just a minute more, please. Sorry.
I'm not really sure like why we're calling that X and not Y. I think I missed something.
Yeah, so we're the first part here, the first trick was to define your X direction as like this, right? That's my X direction. And it's because we're defining the X direction is the direction of the acceleration. And so if you think back to that tip on a previous slide in a previous lesson, it was like the hot tip would be always to define your X direction as the direction of acceleration. Is that helping?
Yeah, that makes sense. Thanks.
Yeah, and I want to just add one more thing, like even with ramps, we define X as this now, right? Down ramp. So same, that's your new go-to move, basically, is define your X direction as the direction things are going to accelerate. All right, so we got a net force of the 88.2. And so then the second trick was that 88.2 net force acts on the entire mass, right? The 10 and the 19 combined. So you have to consider the total mass that net force is acting on. And so we have an equation that looks like this, where we're like, okay, F net equals ma, but instead of just being one of the masses, it's both of them combined, right? That's 29 kilograms. So F net equals ma gives you an acceleration of 3.04. So the way we've walked through this, I think you'd find I'll reveal these steps here from this one if you want, but oh my, it's to me like it's much harder to follow the way they've described it, where I'm just saying like, hey, these two forces are just one's up, one's down, essentially, right? One's forward and one's backwards based on my direction system. So easy peasy, not actually too bad. So let me know when you're. Does anybody need time for that slide right now?
I'm good. I'm not sure, but
Thank you. All right, so I'll leave the bottom of it visible anyways, but we've got that 3.04 meters per second squared acceleration value. If we're asked for the tension in the cables here, what's the tension in these cables, then we can actually just analyze out the net force for each one, right? So we could analyze M1 if we wanted. M1 is this one, the 10 kilogram. Okay, when we analyze the net forces on it, there's going to be a tension force up and there's going to be a gravity force down, right? So picture there's going to be a tension force here, FT1, right? And a gravity force, FG1. So we can just analyze the net force there and say, okay, well, this thing's accelerating at 3.04, right? And so F net equals ma right? So we've got an F net equals a 10 times a 3.04. That's the acceleration times the mass of M1. And we're saying that there's a gravity force and a tension force on it. And so the gravity force for M1 is in the negative direction, right? Because in the analysis on that side, the x direction is up because it's accelerating up. So that clearly makes us be able to solve for the tension force, right? So we end up with the tension force being 128.4 newtons up. Okay, in the positive direction, essentially, on that side of our reference system. It's like if we're thinking of this as like there's a tension force there, and it's I don't know how to say this. I want to just say, like, if there's a pole here in the rope of 128, then obviously there has to be a pole of 128 in the other end as well. You're attached by a rope, right? Like tension at all points in the rope are going to be the same. So I can actually work sort of backwards here if you want, point out that the answer is going to be 128. It better be, right? It's just that it's going to be up, isn't it? Because on this side of the system, we're talking about an upwards force. That's actually a negative on this direction system. So if we were doing that from scratch, this is either or, right? So you can look at either one of the masses. So we can look at mass 1 and get the tension force that way, or we can look at mass 2. With mass 2, you just have a different value for mass and acceleration, or for the mass anyways, not the acceleration, of course. So it's accelerating at 3.04 still, of course. Notice that these are both in as a positive, right? The 10 times 3.04, the 19 times 3.04, because they're both in the positive direction. By definition, the direction of the acceleration is the positive direction, right? So even though we're flipping, one's up and one's down, we're sticking to our definition here of the direction system. So the gravity in this case goes into the positive, right? So this guy is in the positive direction based on our direction system. It's in the same direction as acceleration. So then that allows us to solve for the tension force. And it ends up being a negative value naturally as part of our work here. So we're able to solve for the tension force even. So this is, this one or this one. You don't need to do both, right? So it's I suppose it's a good confirmation, if one or the other or both, but if you do the second one, think of it as like a check. You should be expecting this result, right? So possibly you'd look at that as a check. But really, you don't need to do both. It's actually a sign of someone not understanding what they're doing if it indicates if they look like they think they need to do both. So watch out for that. You could just make it clear that you're doing a check if you're showing both. Worst is if someone calculates this, gets an answer, and then does this one as well, not realizing they don't need to, makes a mistake and gets a different answer, and then concludes, oh, therefore the tension here is 128, and the tension here is 242, and be like, yeah, that's not up. That's not happening. You'd be breaking that rope, really, is what you'd be doing. All right, so that is the so-called Atwood machine, which is obviously a fairly common situation. You get a pulley and two things hanging on either side. It's not a balanced situation. It's going to accelerate. This is exactly how it will. This is the analysis of how it would accelerate. A more common situation than this one is this, and I don't think this one has a special name. This is just a pulley hanging over a table causing acceleration. All right, so we can do this with the smart cards if we wanted to check numbers and so on, and it would work really, really nice. So maybe that's something we get a chance to do. For now, we can look at the numbers of this, and that, to be honest, this course would normally be focused on the calculations anyways. Grade 12 is just a more theoretical course. So it's not that much different being online. That's what I'm saying. So we got a 1 kilogram cart. We've got a 0.8 kilogram block hanging over the edge. Now, the same thing as before. Once you figure out Fnet acts on both masses. Fnet acts on both masses, right? So M1 plus M2, obviously here is like 1 plus 0.8, right? So we're talking about a total of 1.8 kilograms. That's going to be in our calculations. We're going to be using a 1.8. You have to remember that, okay? That this gravity is accelerating this thing, but you know this mass and this mass both need to be accelerated. So you can't just think of this as a tension force. It has to be you have to include that mass. So the calculations, obviously we know we're given the masses and we're required to get the tension force, the acceleration and the tension, I suppose. So the analysis of this, let's go to the, is this the one where there was, maybe not, yeah, 2 pages down. I want to go to my nicer solution of this. Just find it. This one here. So X direction system, right? Define your X direction with a bend. The pulley makes it bend, just like the other pulley, okay? So we've got an over and down X direction, positive direct X direction system. So we know, we've got a net force in the X, yeah, the net force in the X direction is just that gravity, right? That's the only force that's acting in this X direction system. There isn't any forces acting. There is a gravity force on this thing, right? But is that gravity force in the direction of this acceleration? No. So it doesn't matter, right? So Fg is not in the direction that we're talking about, right? This is not in the X direction. So it doesn't contribute to the acceleration. Only this gravity is here. So this Fg is in the system, Fg, right? This one actually provides the acceleration. So we can do some calculations. We've got, oh, and this is the other part there about the masses, right? So F nets on the combined masses. And so we can plug numbers in. So we've got the 1 and the 0.8 and the 9.8 and so on, all just plugged in. Notice this is going in as a positive here on purpose because it's in the direction of the positive acceleration direction. So that mathematically just solves out lickety split for a 4.355 ... You know, keep however many digits you're supposed to keep. 4.4, rounding up to be an even number there for the 5 rule. So we've got an acceleration calculated. So this is, you know, like we could literally do this. If get the cart, add some mass. I think we have to add 500 grams to it to make it be 1 kilogram, hang a 0.8 kilogram over the pulley, measure the acceleration and see how close it is to 4.4. I think the hard part would be getting this to be exactly 1 kilogram, to be honest. So instead, I'd probably measure what it really is and calculate what the acceleration should really be, and you'd be surprised how accurate it is. Maybe not though, because you've seen these things, how accurate they are. So tension, how do we get tension? You can analyze either one. Right? So if you looked at mass C, right? The tension force, it's the easier one, right? Because it's literally just the tension force is the net force. Right? Do you recognize that looking at it? You're like, the tension force on here, there's only one force on it, right? So the net force must be the same as the tension force. So we can just do the math. We've got F net equals now the weird part, remember we looked at F net equals the combined masses times the acceleration. Now we're just talking about the net force on the single mass, right? So it's just the mass of the cart times the acceleration. The acceleration is still 4.4, but now we're talking about a mass of 1, so it gives us the tension. Tension force is 4.4 newtons. If we calculate the tension force based on the other one, we better get an answer of 4.4. It's just going to be the opposite direction, right? So if you decided to look at that cart, or that mass, sorry, obviously it's a little bit more complicated because we've got, I'll just reveal it bit by bit here. We've got just more forces going on. So you'd have to realize like, oh, we got the net force on mass B, MA. We've got the gravity force and we've got the tension force. So the gravity force is in the positive direction. The acceleration is in the positive direction. That's a little weird, right? Watch for that. Like that we put this in as a positive value. It's in the direction system. It's in the positive direction. So that's different and a little weird, but it's just an analysis that makes this easy to follow. So we end up, I'm keeping the significant digits there. I much prefer just to keep all the digits till the end, of course. Yeah, solve out. You end up with the minus 4.4, meaning, of course, it's up, right? All right, so, this is the 2-mass system I put in there. Remember this stuff from grade 11? What are the tensions between the blocks? You still need to be able to do that. You need to be able to do it in grade 11. So if you need, there's an example worked out there for that. So I will be PDFing this and posting it for you to use, work on. So the applying Newton's laws stuff are these ones here. And that is your 2 lessons of physics for the day.